In part one of this series, we ended the story with the formation of the first stars in the universe. And under the influence of gravity, those clusters of stars merged into larger collections that we call galaxies. And with the modern Hubble Space Telescope, we also now understand that our visible universe is populated with hundreds of billions of galaxies, and our Milky Way galaxy is just one among many, many galaxies in our universe. We'll pick up the story then with the formation of heavier elements by these first stars. And this is an important event because at this stage in the universe, the stars, of course, are composed of the two simplest elements that are in existence at that time, hydrogen and helium, with more hydrogen than helium existing in the universe. So all of the rest of the elements on the periodic table of elements did not yet exist. So these first stars, composed of hydrogen and helium, these celestial objects are going to be responsible for building all of the heavier elements that we know about in the periodic table. So here we see our sun on the left, and we want to think of the sun and the rest of the stars as element factories. They're going to be building the atoms that will make future planets and life, at least as we know on one of those planets. So how does a star make a heavier element? Well, let's go up here to this diagram. Here we have our star, and we have learned already that the star was fusing hydrogen nuclei into helium nuclei, and that released energy. And the fusion energy was tending to expand the star, but gravity was counteracting that, and the star was balanced. The two forces were in balance. But what happens when the hydrogen fuel runs out? So the energy from the fusion is going to diminish. It will decrease momentarily, and that allows the same gravitational force to squeeze and compress the star even more. Well, when you compress that volume of hydrogen and helium even more, although the hydrogen has run out, when you compress the star even more, the temperatures get even hotter, the pressures get even higher, and now you get to a point where you can fuse helium nuclei into the nuclei of heavier elements. So let's take a look. Here is our diagram. We have 3 helium nuclei, and the idea is under high temperatures and pressure, these nuclei can fuse to form the nucleus of a heavier element, in this case carbon, with 6 protons, 6 neutrons, and here we would see the carbon atom here. But of course in the star it's a plasma, so the electrons are not in orbit around the nucleus, but this would be a carbon atom. 6 protons, so its atomic number is 6, and it's got 6 electrons surrounding the nucleus, and that nucleus was formed from the fusion of 3 helium nuclei. So we've seen this picture before, so take a look at hydrogen here and helium. When the star has hydrogen, the star is fusing hydrogen nuclei to form helium. But when the star runs out of hydrogen, the star is using this heavier element, helium, and fusing it with other helium nuclei to make even heavier elements. So this is the same story here. Stars are using lighter elements, fusing them together to make heavier elements. So again, when we look at a star or think about a star, we want to think of these celestial objects as element factories. They are responsible for creating the rest of the elements on the periodic table of elements. Now in this diagram we see some possible fates of stars. We have a cloud of gas over here, of hydrogen here, that will be the material to make the star. Gravity will collapse that cloud to make a star. If it's a small star, it has a particular destiny. If it's a large star with a lot of mass, heavier than the sun, when those stars undergo nuclear fusion and then run out of fuel for fusion, they explode in a colossal explosion called a supernova. Now, why this is important is because the supernova explosion itself is responsible for creating a lot of the really heavy elements on the periodic table. The normal fusion sequence in a big star like this, they make lots of elements up to iron, but elements heavier than iron are created in these explosive events called supernova. And also importantly, when the supernova happens, all of the elements in the star and those created during the explosion are distributed back out into space. And these are the elements then that will be incorporated into newly forming stars and make possible the creation of rocky planets like the Earth. Recently, the Hubble Space Telescope took a picture of a galaxy that is some 60 million light years away, and they caught a supernova. That little white spot there is a supernova, a very bright event when a star goes supernova. Here, the Crab Nebula is a famous example of the remains of a supernova. So when we look at this kind of nebula, we want to think about all of the diversity of elements that are present in the remains of this supernova. So the star made a bunch of elements during the normal course of fusion, and in the explosion itself, even heavier elements were created. So this nebula is rich with lots of different kinds of elements, atoms of different elements. In this diagram, let's take a look at the left here, and then we'll get to this picture here. Let's see the significance of these supernova over time. Recall in the early universe, the universe was really just a giant cloud of hydrogen and some helium, right? Well, gravity takes hold of those gas clouds and compresses them locally to forming stars. Stars undergo fusion but then run out of fuel. The big stars explode in supernova, and so now we start to populate that same nebula, that same cloud of gas, with heavier elements. Well, new stars will be forming over time, second generation stars, and those stars will actually have some of those heavy elements incorporated into them. But again, it's mostly hydrogen being fused into helium, but when the nuclear fuel runs out, the big stars go kaboom and distribute even more heavy elements back out into the gas cloud. So after several generations of stars and supernova, and new stars and supernova, what you end up having then is a cloud of hydrogen gas that is rich with heavier elements. And that's exactly the material you need to make a solar system. So the hydrogen gas will be incorporated into a new star, but the heavy elements will be the building blocks to make minerals and rocks and rocky planets like the Earth. This picture over here, taken by the Hubble Space Telescope, just shows a star-forming region. So new stars are being made in this region, but we see all of this other dust, this gas and dust. So most of that is hydrogen, but the dark regions here, this dust out here in this nebula, would be composed of these heavy elements. So let's get a sense of how much material we're talking about. Here is a supernova remnant, Cassiopeia A, and scientists estimate that that supernova ejected 70,000 Earth masses of iron and 1 million Earth masses of oxygen. You'll recall, here's the Earth over here on the right, and here's a breakdown of the most common elements in the Earth's crust. Notice iron and oxygen are common elements in the Earth. Well, one supernova created enough iron to make 70,000 Earths. One supernova created enough oxygen that could be present on 1 million Earths. So we're talking about huge quantities of these heavy elements, right? And if you have multiple supernovas going off over hundreds of millions and billions of years, you're going to have lots of materials to build rocky planets. So we want to think of rocky planets as being composed of star stuff, the elements that were forged in the cores of stars and also in the explosive eruptions called supernova. So let's back up here and let's define some terms here. So we'll say that a nebula is a giant cloud of gas and space dust. Previous generations of exploding stars have enriched the nebula with heavy elements. The material in a nebula can be incorporated into the next generation of stars and planets. So here are two very well-known nebula, the Horsehead Nebula and the Orion Nebula. And what you're seeing here, this kind of colorful region of gas and dust, this is the stuff out of which new solar systems could be made. So most of the gas is going to be hydrogen, and the dust is referring to these heavy elements that make up lots of the material things that we're familiar with on Earth. In fact, the Horsehead Nebula is thought to have enough material to make 30 suns, 30 stars, and rocky planets. So the gas in the nebula is mostly hydrogen and, of course, some helium. The space dust is the diverse collection of atoms of different elements and small molecules made from those atoms. Space dust includes tiny particles of matter smaller than a grain of sand, often bits of rock or carbon-rich soot-like grains. It can also include frozen water, carbon dioxide, and other forms of ice. So it's material stuff. And we see it in these beautiful pictures of nebula as this colorful gaseous stuff, but you can kind of see that it is dark. The regions where it's concentrated, those are dark regions that are blocking the light from stars that are behind those regions. In fact, we can see this in a picture of our Milky Way. We see these dark regions in the picture. Here's a dark lane of dust here. Here's a dust lane here. Now this dust, again, is not dead skin cells. That's a lot of the dust in your home. This dust would be heavy elements and small molecules and small particles of matter. On the left here, here's our sort of drawing of the Milky Way. And again, when we take a Milky Way photo, we're looking towards the core of the galaxy. Here on the right is a picture of our galaxy, again looking towards the core right here. And again, these dark areas would be the dust that is present in one of the spiral arms of the Milky Way that is between us and the core. So this dark lane here would be one of the spiral arms of our galaxy that has lots of dust. And so it appears dark because it's blocking the light from stars that are behind that arm. We can see some of the brighter regions of the core here down here. So this is the combined light of millions and millions of stars. But this darker region here would be dust that is blocking the light from the core that is behind it. And early in the universe then, in the first galaxies, of course, there wouldn't be this dust because we didn't have enough of those, of multiple generations of stars and supernova to explode to create all of this dust here. So in the early universe, you wouldn't have these dust lanes. Those elements would not yet have been made. All right, let's just briefly talk about atomic structure as it relates to the chemistry that occurs in space. So here we have our picture of some atoms, and we show that the nucleus of the atom has a certain number of protons. That defines the identity of the atom. And also notice now that the number of electrons orbiting the nucleus is equal to the number of protons. So helium has 2 protons, 2 electrons. Lithium 3 protons, 3 electrons. Oxygen 8 protons, 8 electrons. And remember, we're not showing the neutrons in this diagram. Now, you'll learn in chemistry class that the number of electrons in these sort of shells, as they're called, influence how these atoms can join together to form more complex structures called molecules. So the world of chemistry is all about how these atoms, as they interact with other atoms, sometimes they join up, they link up, they create chemical bonds. And the structure of the atom determines how the atom links up with other particular atoms. Now, on the left, let's remember a supernova has exploded and has distributed lots of different elements back out into space, and this sets up the conditions where chemistry can occur. Chemistry involves atoms joining together to form molecules. Now, how does this happen? Well, up here at the top, we see the formation of a chemical bond between 2 hydrogen atoms. Let's imagine 2 separate hydrogen atoms are going to collide here. In that collision, the atoms are brought close enough that the nucleus of one of the atoms can actually attract the electron of the other atom. And the nucleus of the atom on the right here can attract the electron of the atom on the left. And so what we have is sort of a shared pair of electrons here. The electrons spend some time around this atom on the left and some time around this one on the right, and that links together these atoms. That's called a chemical bond. The 2 atoms are sharing their electrons. We call this a molecule. So a molecule is composed of multiple atoms joined together by chemical bonds. Well, the supernova has distributed all these different kinds of atoms out into space. When they're bumping around, they can link up with different atoms and form different kinds of molecules. So we're calling this chemistry occurring in space. And there's lots of different kinds of molecules created because there's lots of different kinds of chemical elements, lots of different kinds of atoms whose atomic structure determines how they can interact with other atoms. Now, just to mention what it is we're looking at down here, let's take this molecule down here. This is an oxygen atom making two chemical bonds with two separate hydrogen atoms. This is a molecule of water. So that bar there represents the sharing of a pair of electrons between this oxygen atom and that hydrogen atom. It's what we see up here where the pair of electrons is being shared. Sometimes they're around one atom, sometimes they're around the other atom. So the oxygen atom, if you take a look, it tends to make two chemical bonds. So here's an oxygen atom making two chemical bonds with another oxygen atom. So it's sharing two pairs of electrons. Here's an oxygen atom making two chemical bonds with a carbon atom. So the carbon and the oxygen here are sharing two pairs of electrons. Notice the carbon atom tends to make four chemical bonds. So this carbon atom is making a chemical bond with this hydrogen atom, but also a chemical bond with three other hydrogen atoms. Here the carbon is making two chemical bonds with one oxygen, two chemical bonds with another oxygen. So carbon tends to make four chemical bonds, oxygen tends to make two chemical bonds, and hydrogen tends to make one chemical bond. Here the hydrogen is simply making one chemical bond with the carbon. Here the hydrogen atom is making one chemical bond with the oxygen. So the different numbers of chemical bonds that different atoms make has to do with their atomic structure, the structure of the electrons in the shells surrounding the nucleus. This molecule here is silicon dioxide. So the silicon atom tends to make four chemical bonds similar to a carbon atom. Here we have a nitrogen atom making three chemical bonds with another nitrogen atom. Here the nitrogen atom is making three chemical bonds with three different hydrogen atoms. So this is chemistry. Atoms are joining together in various combinations to form molecules. And so because there's a great diversity of different kinds of atoms, we have a large diversity of lots of different kinds of small molecules here. So when we look at a picture of the Orion Nebula here, this dust stuff, we want to think that it's composed not just of heavy elements. It is composed of heavier elements, but also elements that have linked together to form molecules. So the atoms have joined together to form small molecules. So this dust is not just individual atoms, but also small molecules. And then these molecules can also kind of clump together into small particles. So this dust, again, we want to think about this is the stuff to make rocky planets. Not the planets like Jupiter and Saturn, mostly composed of hydrogen and helium. We're talking about rocky planets that are made from heavier elements. Those heavy elements can also link together to form small molecules, and we'll see that these molecules are the very kinds of things that make up the structure of rocky planets. For example, let's take a look. Here's an artist's rendering of the early Earth. Well, we had rocks, right? A lot of the crust of the Earth is composed of rocks. Well, the minerals that make up these rocks were made in space prior to the formation of the Earth itself. What do we mean by rock? What is a rock? Well, here's Yosemite, and here's El Capitan. This is granite. Right? So what is granite? Here's a picture of a lump of granite here, and you see it has different kind of colored regions here all mashed together. Well, these different colored regions are different minerals: quartz, hornblende, feldspar. And if you take quartz, for example, the atomic structure, the molecular structure of quartz is oxygen and silicon atoms chemically bonded in a certain kind of way, a certain kind of three-dimensional structure. So quartz, a mineral found in granite, is composed of oxygen and silicon atoms. Well, those atoms were formed by stars and distributed out into space by supernova. What about feldspar? Feldspar has a more, complicated arrangement. There are a couple more atoms involved, aluminum and potassium. So we have these complex kind of crystalline structures that form these minerals. So rocks are made of minerals, but minerals are made of atoms that are joined together in certain ways, and these atoms came from stars and then were distributed back out into space. So when we think about the rocks on planet Earth, out there in space we had molecules like silicon dioxide floating around in nebula, and these are the molecules that are going to end up becoming the rocks on planet Earth as the Earth formed from the material in a nebula. What about the atmosphere on the early Earth? Well, those molecules were also made out in space. Here I've circled some of the molecules that you find in some planetary atmospheres: carbon dioxide, nitrogen, methane, ammonia. So the materials, the gases that we find in atmospheres are molecules that are present in nebula. What about the water on planet Earth? Of course, water can exist in gas, liquid, and solid phases here. So we've got ice, the solid phase, water is the liquid water, liquid phase, and then water vapor up in the atmosphere would be the gas phase of water. So we've got lots of water on the planet's surface. Well, this water that makes up our oceans and our rivers and streams and lakes and the water vapor in the air was made in space. So again, out there in nebula, we've got molecules of water. These are water molecules. Now, it's so cold in space that the water in space is in the form of ice. In fact, just in 2020, in the summer of 2020, we had the privilege of seeing an approaching comet. This is Comet Neowise. And comets are frozen gases of various kinds, a lot of water. So, water vapor, water that's frozen. So it's a lot of ice, rocks, and dust. So it's a really cold structure. And sometimes they're affectionately called dirty snowballs. So this is the kind of celestial object that has lots of the stuff that would make the water on a rocky planet. All right, so that brings us then to our next phase in our story here. We've got heavy elements made inside stars and during supernova are going to be ejected back out into space, and that's the stuff out of which rocky planets will be made. We're still in the modern universe here, but now the stage is set to make solar systems, new stars with orbiting rocky planets. We'll pick that up in the next part.